In this tutorial we will see how to use the CTF consensus to qualify the agreement between two different estimates of the CTF. So let's say that we have a set of micrographs that we have just aligned, and we want to compute the CTF using CTF find for instance. So CTF find is normally very accurate in the determination of the defocus, and but it only calculates the defocus, so we cannot estimate the envelope. We see that these tone rings are fading over time, over space, over frequency, and so we could for this particular estimation we could sort by the defoci, for instance. So we see that these micrographs, they have a very bad defoci and they are very much astigmatic. So we can also, for instance, sort by the different criteria, so we can see what is the histogram of the defocus, or we can see what is the histogram of the defocus ratio. So we have the defocus ratio, most of it is around 2%, 3%, 4%, and there are a few of them that are pretty much pretty high. This is the range of defoci, so most of them are sub micron, so this is 1 micron, 10,000 angstroms, and some of them are very much defocused. So we will see now in a moment a tool that allows us to choose the range of defoci that we want. Also this fitting quality. So this fitting quality in principle should be, this is a correlation, so in principle it should be as high as possible. So the highest correlating CTFs should have much better agreement than those at the beginning, as we were seeing. So at the beginning there is very little correlation. So we can see in this histogram that probably these micrographs, either the micrograph is not good or the fitting is not good. So we could have the same with XMIP CTF. So XMIP CTF is the CTF estimation from XMIP, and it has the advantage that it estimates the envelope of the CTF. So in principle the tone rings should fade in the same way as the experimental ones, and we can also sort by defoci and defocus ratio, but there are many more parameters here. So for instance, one of the differences in the estimate of the resolution is that CTF find defines the resolution as the frequency at which the two CTF functions in two perpendicular directions, so the direction of minimum defocus and maximum defocus, they disagree by more than 90 or 180 degrees. I don't know the exact detail, but it is based on the difference of the phase of the CTF. While in XMIP the resolution is defined by the frequency at which the envelope drops below 1/100th of the maximum envelope that we have seen for that CTF. So one is based on the difference in phases, while the other one is based on the amplitude decay. And we have here some other criteria, like for instance the correlation between first and third zero. So in principle it should be as high as possible, and we can sort by this and see that the correlation here between the first and third zero is pretty low. In this particular case it was because of a failure of the estimation of the defocus, and we can avoid these failures very often by starting the CTF estimation from XMIP with a previous CTF estimation. So we can now use the CTF CTF find 4 as the input, so it will start from this the focus, the refinement. But this also may cause a bias. If the CTF find 4 was incorrect, there will be almost no disagreement between the CTF of XMIP and the CTF find 4 estimate. So we will not be able to detect those micrographs for which there is an incorrect estimation. So it is better to have two independent estimates, even if there are some of them that are not so much agreeing. So also we can estimate the iceness. So the iceness is defined as, if we can sort by it, so the iceness is defined as the ratio between the energy that we have at 3 angstroms, at a resolution of 3 angstroms, and the energy that we have at a little bit more. So we can see here, if we go to the end of this list, we can see that there are really crystal eyes. So yeah, this is another way. This non-astigmatic validity is a bit like the phase difference that we were discussing before for CTF find 4. So it sees at which frequency the assumption that the micrograph is non-astigmatic breaks, and this one breaks at 4 angstroms and 4 angstroms because it is relatively astigmatic. And on the other side we should have the most agreeing ones, like these ones. So for some of them, especially for the beginning where there are incorrect CTFs, they don't make sense, but otherwise should estimate pretty well that to which frequency this is good. Then we also have the CTF margin. The CTF margin is defined as how visible the tone rings are with respect to the noise. So here we cannot see the tone rings very well. Here we see the tone rings very well, but they are very astigmatic. And if we go to the other end of the list, we see that the tone rings are extremely well seen. So yeah, there are many different criteria. This one is also very interesting. It is the correlation between the power spectrum density and the power spectrum density if we rotate 90 degrees. So the best correlating micrographs, they are extremely good, while the worst correlating micrographs, they are not so good. So there is no correlation if we rotate this image by 90 degrees. Okay, so the CTF consensus takes all these things into consideration. So the CTF consensus serves to two purposes. So you can even use it without two CTF estimates, just one. So for that one, that is called the primary, in this case I have chosen the XMIP, and you can choose which is the range of the foci that you can you allow to progress automatically, then which is the maximum astigmatism that you allow, what is the minimum resolution or maximum resolution that you allow. So if the resolution is worse than this one, it doesn't progress any further. And if you are using the XMIP as one of the estimates, you can also put limits on each one of these iceness, CTF margin, correction of the first zero, and so on. Then you can also compute the consensus with a second CTF estimate. So in this case we have chosen CTF find 4, and they have to agree, so the two CTFs have to agree up to 10 angstroms. and this is a way of avoiding obvious mistakes between the two estimations. So this CTF consensus will classify the images into agreeing CTFs and those that fulfill the limits and those that don't fulfill the limits. And again, the micrographs are never discarded, they are simply put aside. So now we can analyze this data and decide whether they are good enough, or for instance this one we would have to see which is the reason why they have been rejected, but this one, because the resolution was larger than 5 angstroms, so the micrograph is good but the resolution is not so good. And for otherwise this one there must be some other reason why it has been rejected, and it is all related to the criteria that we have defined. But we see that many of them are either bad CTFs or micrographs for which there is some problem with the estimation.